So what we'll do is we'll keep this kind of informal. We have some slides to go through, and each one of the members of the panel will introduce themselves when they get a chance to talk and talk about the area they're working on and talk about the things that we're doing on station and using station to really advance technology in a real and meaningful way. We have an amazing facility on board Space Station, and we really need to use it from a technology standpoint. I'll start off with some kind of just lead-in slides to kind of set the overall stage. You know, station is really a one-of-a-kind test bed. It's in a position of global leadership. It's a catalyst for the commercial market. It's an engine of discovery, and more importantly, it's a stepping stone to exploration, and that's the technology things we're going to talk about. I also consider it a limited time asset, that we've got to really make sure that the technology and the investigations we do occur in a timely manner such it can affect the exploration activities that are coming in front of us. This is kind of an eye chart, but it shows all the various areas of technology we're working on. Again, you can just look at the variety across the spectrum here, from radiation, fire safety, health and human performance, life support systems. All those are called out in the bubbles that are up here. These are things that we can really do and really need to check out on station. And each one of our panel members has an area of expertise that fits on this chart, and they'll describe their area of technology and activities they're doing on board station. Okay, and again, you know, how this all fits is we're really in this phase 0. This is the ISS phase of exploration. This is where we're using Space Station to resolve these problems. Station is in a great location in low Earth orbit. It's relatively accessible, so we can do technology development and discover things. So everything doesn't have to work perfectly on station. We have a chance to, if it doesn't work, to fix it, to repair it, and get it ready to go. But by the time we move to this phase 1 region around the moon, we'll carry some of those same exploration systems, but the phase 1 area around the moon is not a good place to do hardware development. It's much better to do that in low Earth orbit, learn these things now. And then when we get to phase 3, when we're going beyond the Earth-Moon system, all these technologies and systems have to be fully functional, fully operational, and ready to operate and ready to move forward. So this is the basic plan, the basic approach we're doing, moving human presence in the solar system. And the first step is really using the space station to build the technologies, build the techniques that allow us to move human presence into the solar system. All right, so with that, we'll go ahead and start with Robyn, and then each one of the presenters will give you a little bit of information on their technology area.
Okay. Good afternoon, everybody, and thanks for hanging in for our panel. I'm Robyn Gatens. I'm the Deputy Director of the International Space Station Division here at NASA headquarters. I work for Gerst and Sam Shamimi. And the other hat I wear is I'm leading the system maturation team for the environmental control and life support systems and environmental monitoring systems. So I'm going to talk initially about overall using the space station as a test platform for our overall habitation systems, and then kind of give you a big picture what we're doing specifically for life support and environmental monitoring. So when we think about this slide just shows the gap today between the systems that we have today on the space station for habitation systems and what we need to go future deep space explorations and missions and on to Mars. The habitation systems include like the life support, the air, the water, the waste management. Today on Space Station, we recycle a little bit less than half of the oxygen from the air system. We remove carbon dioxide and we recycle back about half of that oxygen. For future space missions in the deep space, we want to reduce the logistics associated with that resupply. So we think we want to get to at least a 75% what we call air loop closure. Similarly, on the water system today, we recover about 90% of the water, and that sounds like a lot, but that still carries a logistic penalty with it that we want to do better for future missions. So we're trying to improve that to over 98% of water recovery and also reduce the expendables associated with that system. And then the big thing that we're trying to do on the life support system is improve reliability, because we have a healthy supply chain carrying spare parts. If something breaks, we can launch a spare on the next cargo mission today on space station. But for a deep space mission, once we send the crew off with spare parts on board, that's what we've got, unless we can print it. So we really want to improve the reliability. We have some things on station today that are failing sometimes less than 6 months, and we really want to improve that. On the environmental monitoring, today we have some onboard capability, but we still rely heavily on sending samples back to the Earth for that detailed chemical analysis to identify what's in our air, what's in our water, our microbial species. And so overall, we want to develop a suite of sensors that we can do all that on board, that we can verify that the water is safe to drink and the air is safe to breathe, and then practice using that on station. And then logistics, you don't think about logistics as, it's not as sexy as the other areas maybe, but it's really important. Because today we have a way to get rid of trash on station. We put it in a cargo vehicle and it burns up and we get rid of it. But on a long duration mission, that's going to accumulate. We need to think about clothing. We can't replenish the clothing, so we need longer wear clothing. And then a way to repurpose materials. So those are some of our gaps that we're trying to solve. And then, so you might ask, well, how are we doing that? This is a really busy chart that tries to put all the activities and kind of our overall plan onto one page. And there's even more activities that I can't fit on this page. But our overall approach is we're evolving the space station habitation and life support system that we have today and what we're calling our exploration system. So we're not launching an entire new system to space station. We're really basing our system off what we have on station today and then closing those gaps. Those new capabilities are improving what we have. So, and we've got if you look at this diagram, everywhere there's a black diamond, that's where we're making a decision. So today we might have several technologies that we're considering, and we're going to make a decision or a down select between those. And everywhere you see a black arrow pointing up, that's where we're planning to fly a technology demonstration to station. So we've already started, and I'm going to show you some pictures of some hardware we've either already flown or have in production now, and we'll be flying over the next year. So this is an evolution, and we're planning to have everything up there by 2021, 2022. So then we start the clock on a long duration integrated test of our exploration system, because that reliability piece is so important and we have to do this long duration test. So this shows some images of some of the things that we have in work. We have today on space station, that part of that 10% water that we don't recover is in the form of a leftover from our urine processor called a brine. We're going to be trying to recover the water from that brine through a brine processor assembly. That's going to be flying next year, and that's being built by Paragon. The spacecraft atmosphere monitor is a micro GC mass spec that's going to analyze both our major constituents and a whole host of trace contaminants. And that's going to provide a lot of capability for atmosphere monitoring. We have our, what we're calling our universal waste management system. It's a toilet. And we're going to be flying that as a technology demonstration, and also it's going to be used in the Orion. And it's going to sit side by side with the Russian toilet we have on station today. And so some of the images there show we're having to provide a bump out. We're having to get creative to fly some of these pieces of hardware and add them to station. So we're going to have these two side by side. You heard earlier today when Kate Rubens was talking about the DNA sequencing. Well, we're developing technologies to use that to monitor microorganisms in air and water and make sure that we know what's in those samples. And We flew a couple of things. The mini-ion DNA sequencer was highlighted earlier. We also flew a device called RAZOR, which is an off-the-shelf PCR instrument. And then our logistics folks flew an RFID-enabled logistics measuring system we call REALM. It's that uses RFID technology to track where things are on the station. We've already found some lost items using that system. And the last image shows an aerosol sampler. This is to monitor the particulate load and to really characterize that load on the station. So it not only informs our filtration technologies that we need to design, but also how to monitor the particulates in the atmosphere and alert the crew if there's a respiratory hazard, particularly when we start doing surface missions with lunar and Mars dust. And then finally, I just wanted to highlight the importance of why do we do all this on station? Why can't you just do all this in a ground test bed? When we flew the regenerative ECLIS system, it's been 10 years now since we flew the oxygen generator and 8 years since the water system. It was really still experimental. And we've learned a lot, and we continue to learn a lot. And we've kind of book-kept some of the things that have happened and asked ourselves, would we have learned that if we had just tested it in a ground test? And the answer is usually no. Either the environment of the space station was too unique, or the combination of the actual interfaces that the hardware had, or the problems just took too long, a really long time to manifest themselves, that more than likely we would not have uncovered those on the ground. And you think, I'll just pick a couple. Our urine processor initially, when we ran it at its design point of recovering 85% of the water, we had a precipitate come out and fail the hardware. Turns out that because crew loses calcium at a higher rate on orbit, that reacted with our pre-treat chemistry to produce a precipitate at the concentration we were trying to run the urine processor at. And that was a problem we found on orbit we would not have found on the ground because we didn't understand that chemistry. So I just wanted to emphasize the importance for these habitation systems of using the space station as a test bed. For us, it's very, very critical. With that, I'll hand it off.
Okay, thank you. And my name is Bill Paloski. I'm the director of the Human Research Program. I also work for Gerst, but my program is hosted at the Johnson Space Center, mainly because it's close to the astronauts and to the space medicine professionals. So, some of you researchers out there might wonder why HRP research gets such high priority on the station, especially because most of you probably think that your science is better than our science, like researchers are wont to do. And most of you engineers are probably wondering, why does Gerst give Bill this money when he's got rockets to build? So, there's one main reason for that, and that is really that getting people safely to Mars and back is hard. It's a lot harder than going to low Earth orbit. So we have identified, and we work closely with Space Medicine and the Health and Medical Technical Authority to decide what the risks are that crew members are exposed to. And it starts with stressors. We have 5 primary stressors that are roughly orthogonal to one another. There's not a lot of interaction between them. All of them are harder in deep space than they are in low Earth orbit. So altered gravity fields in hostile closed environment, and you just heard a lot about how we're dealing with hostile closed environment from Robyn, are somewhat harder, mostly because we're going to be there for a much longer duration. Radiation, isolation, and confinement and distance from Earth are a lot harder than in low Earth orbit. And I'll talk a little bit about why that is. The actual work that we do is structured as risks that are monitored by a board, the Human System Risk Board, that includes a lot of operational folks as well as research folks. And the risks are broken down by the stressors here. The ones that are in black on this chart are ones that we have a pretty good handle on, and we think we've kind of burned down probably to an acceptable level for exploration. We have some more work to be certain that it's going to be an acceptable level for exploration. The ones that are in red are ones that are sticking out. They're ones that still need a fair amount of work to do, and we have a lot of work that needs to be done before we're going to be able to fly folks to certainly beyond the Mars or beyond the lunar environment. So most of that work is scheduled. The plans are scheduled. It's hard to schedule research, but we have an idea of what it's going to take to do those. We use, in addition to station, a number of analogs on the ground to carry out some of this research, especially for radiation and isolation and confinement. The outcome of our work is a set of operational requirements, and the hardest requirements, and the ones that are going to be needed the soonest, are the ones that affect the vehicles that we're going to be using for deep space exploration, both the Deep Space Gateway and the Deep Space Transport. Probably the things that are associated with most of the hazards are things that we've already been doing for many years on station. They might have to be a little bit heftier, a little bit bigger. The primary one that concerns me the most right now is the one about distance from Earth, because many of the functions that we've done in the past with a lot of interface with the ground, and knowing that we had, for instance, with the medical system, a bailout plan. If somebody really got sick, we could deorbit them. Disappear when you're on your way to Mars. As soon as you burn for Mars, you're going to Mars. You're not going to have resupply. You're not going to be turning around and dropping somebody off, so you have to take care of people while you're there. So those autonomous operations all have the potential to affect the vehicle. The rest of the stuff that we work on is going to be countermeasures and procedures and approaches to dealing with issues that come up. And those things can come later. They can become crew support equipment or just operational procedures. I want to give you an example, though, of the difference, at least as we see it today, for the medical system. The exploration medical care concept on the left. And by the way, this is a work in progress, so don't take as truth anything has not been through a board yet, but it's just for example. Compare the complexity of that system with the low Earth orbit system we have on the right. What we've evolved to on the right is a small countermeasure set, some exercise devices, some environmental health monitoring and alarms, and then a crew health system that's basically a black bag, a med kit for the crew members. But we also have the two things I talked about a few minutes ago: the ability to deorbit if we need to, but a lot of conversations with the crew surgeons in real time to work through problems and to try different approaches before you have to do that. On the left, in the yellow box, that's going to replace what's in that low Earth orbit box. There are a number of systems we have to fly that have to work autonomously. We'll probably need some kind of an artificial intelligence interface, like we heard the IBM guys talking about earlier, whether it's Watson or some other project. But we're going to have to be able to query the environment for what's going on. But we're also going to have to think about how to take care of people. And even if your crew of 4 has a physician, Murphy says that the physician is the one that's going to need the care. So you're going to end up having to go to an engineer or a geologist to provide that care. And how are they going to diagnose the problem with a 20-minute time delay from Earth? You're going to have to be carrying that stuff aboard. So this is one of the long poles in the tent that we're working on. Most of the piece parts that are shown in that yellow box are being tested one at a time on station so that we understand how they work. But the whole integrated system will have to be integrated with the vehicle as we go forward. We pay a lot of attention to the artists and the dreamers, and the Hermes vehicle that was presented in The Martian is probably the dream for all of the medical and research professionals. It has a lot of space. It has all sorts of space for storing food and for separating out work areas from play areas and private areas from public areas. It has a rotating segment that can provide gravity or a gravity supplement. It has a lot of solar panels, so there's a lot of power. So there's a lot of mass, a lot of volume, a lot of power, a lot of capabilities. We sort of think of this in terms of the top-end Lexus SUV model that we'd like to fly. And what we're actually going to fly is probably something that looks a little bit more like this. It's really going to be more like a smart car or maybe a bicycle. So not only do we have a real challenge to try and add new things to our toolkit, but we have to make them smaller. And in a minute, Bobbie Gail's going to tell you a lot about how we do that. I wanted to just end, though, with telling you where we're going in the future. We continue to be one of the heaviest crew utilization research groups. We have between 30 and 50% of the utilization time on any particular increment. All U.S. crew members sign up for some of our experiments. Most U.S. OS crew members sign up for some of our experiments. And through the one-year mission program and our previous relationships in the Phase 1 program with the Russians, we have a number of Russian cosmonauts who are working on joint experiments and sign up for our work as well. We do need to start expanding the stressors on the crews so that we know that we can actually get safely to Mars. And we can't do it all with 6 months missions and then jump to a single one-year cislunar mission and then a 2-year Mars mission. We have to step our way up. So we've proposed, and we've been working with the station on a set of additional one-year missions. We need 10 crew members before 2024, so there'll be a lot of this coming. We'll have a research solicitation that goes out this fall in anticipation of perhaps doing the first one in association with the commercial crew, with the advent of commercial crew in a couple of years' time. We will use those missions to validate that we have the right incidence, that we have the right understanding of the time constants of changes in the physiologic systems, and that the countermeasures that we've been developing are all workable. So this is where we're going to be going. You can expect to hear more about that in the future. The first twin study, the first year in space study was quite a success, and now that we know how to do it, we need to go and get a big enough end that has some meaningful data and know what to expect in the breadth of the astronaut corps. So.
Thank you. What did you do? Press that? Mm-hmm. Okay. I'm Bobbie Gail Swan, and I'm Assistant Director of Integration for Human Health and Performance, and I'm also the Crew Health and Performance System Maturation Team Lead. Let's see, let me go to my charts. All right. So the Crew Health and Performance System Maturation Team is centered around the human system risk, which Bill just told you about. What we're doing is we're integrating the research roadmap with our technology roadmap, because that is very important to formulate the mitigation plans for these human systems risk. So I'm very well integrated with the human research program and what we're doing, because we need to operate hand in hand. And I'm also integrating with Robyn, because a lot of buying down on Robyn's roadmap requires data from the human health and performance system managers. And so we are working very hard to stay integrated and to cover all the bases as we move forward to exploration. We have divided the risk into categories, and these categories map up with the human research program's element managers. All of these categories we are using Station for to advance our technologies, and I'm going to talk to you about two of them in two of the categories and stuff that we're doing on Station today. The first one has to do with radiation, and I'm going to have to use my hands. I guess y'all can hear me, because I need to walk too. I mean, I don't know how y'all do it, just sitting here so still. Okay, because you start getting excited about this, right? Because if you notice on the station, a lot of the radiation monitoring capability we have is like a passive box that hangs off the wall that every so many months we have to move it to a different module to characterize the radiation environment. Well, through our partnership with the University of Houston and their membership in a consortium at CERN, we were able to get access to a sensor that's the size of your thumbnail that will monitor, that we packaged to monitor radiation. And so we packaged it in a thumb drive, and using the computing power on Station, we have deployed these thumb drives throughout Station and are actually doing active radiation monitoring. So we're going to be using that technology. We've been able to prove out that technology, and we're packaging it to where we can use it on Orion. What do you mean? Orion's not going to have a bunch of computers deployed up there. So what we're doing is we're integrating the sensor and the system into the vehicle power and data system. So we won't have bulky things hanging off the wall. We are now moving forward, right? Because we're going to have a smaller environment. So then we said, oh, beam's coming, an inflatable system. So we said, let's move a couple of those thumb drives over to beam and take the measurements inside a thinner shell. And that was the first time that NASA measurement of radiation fields inside of an inflatable module was done. And so we moved a couple of those thumb drives over there. And then as we started getting the results in, we said, this is some low energy particles coming through there. We know how to shield it. Oh, there's polyethylene, a material that can be used that we're well aware of for shielding radiation, and they have it with a 3D printer. So we went and printed out 3 spheres out of 3 different thicknesses to work out what do we need to add to shield in a thin shell environment, and that's what we're doing right now on station. And so, oops, I gotta have this. So if you look here, you can see the little white sphere in the middle. That's the polyethylene sphere that we've got in one of the thicknesses. And right up at the top of it sticking out is our thumb drive that has the radiation monitoring sensor on it. And so we put the sphere on one of the 2, and we're taking those measurements right now. So again, we've gone from moving a passive box around to active monitoring to where we're going to use it on Orion, and we're going to integrate it into the vehicle power and data system. And now we're looking at shielding techniques so that we can learn more about sheltering for exploration. Other area that we're actually using station heavily for is exercise. We have a suite of exercise devices on station right now. We know that that maintains crew health. With the experience from the Human Research Program and the data that they've gathered, they have come up with a potential solution for exploration, and it's called ATLAS, and it's the Advanced Twin Lifting and Aerobic System. It has a aerobic and resistive capability. It's going to be doing lifting and rowing, and we are developing that now to fly on board station in 2020. I'll show you a picture. So, I will in a minute. There you go. So the ARED, the T2, and the CVIS are the 3 exercise devices that we have on station today. Altogether, those are about 4,000 pounds worth of equipment. The ATLAS concept, which we're looking at for exploration, is total of 200 pounds. It's 150 pounds for the device, 50 pounds for the accessories, and the plan is to store the accessories in the base. Right? That makes sense. We're not going to have the room to have all the suite of exercise device. We need to maintain crew health, and so we're testing on station this device to see if that's going to be what we use for exploration. The struggle is real, as Bill said. We are making great progress of going and using station to go from a lot of room to this little bit of room, and I think we're making some good progress. I think we've proven it with the radiation concepts and stuff that we're testing out right now, and hopefully with the exercise device. And we have, and I could go through every category to where we have stuff, because the piece parts that he's talking about for the exploration, medical, and stuff is all stuff that we're working on hand in hand.
Okay, thank you.
Ooh.
I thank you. All right, could have been for you, Mr. Fire.
I don't think so. My name is Gary Ruff. I am the Spacecraft Fire Safety System Maturation Team Lead, and also the project manager and co-I of the Spacecraft Fire Experiment, or SAFFIRE. For a while, Bobbie, Gail, and I were funded by the same program, and I always got to talk after her, so I got to be more animated also.
Just take it.
We have our fire safety gaps and capability gaps, and they're listed on this chart. They really can be broken into 2 categories. Equipment that we have to provide the crew to make them safe on a long-duration mission, and then things that we have to know to either incorporate into the vehicle or into the design and supply information to designers to make it better. You can see there we've got fire suppression and emergency crew mask, combustion product monitoring. All those are things that we have to give to the crew. Post-fire cleanup or a smoke eater. to give them some way to respond to a fire and clean it back up, if that would occur. Some of the knowledge gaps really come from low and partial gravity material flammability. That gets really to the upfront in the experiment or the vehicle design of what materials am I putting in there, what materials shouldn't I put in there, and what is my risk then of a fire, if I have to use some type of material. One of the big things there is partial gravity, which we struggle with. We know there's a difference, but we don't have a really good place right now to test that. One of the other areas that I want to highlight is just the scenario modeling and analysis. One of the questions we get a lot during vehicle design is, well, how long is it going to take for my smoke detectors to alarm? Or what level should I set them at? Or what's the pressure and temperature going to get in my vehicle if there was a fire? All of those things, we can use tools to predict that, but the real key is, we've got to have them validated and know that our models are good. One of the other pieces to note from this chart is if you look at the need, many of the fire safety needs are not things that we can really develop with time. Cislunar, okay, but I have to have that there, but I also have to have those systems on Orion. And having that consistency of an emergency response system, such as some of these fire safety components, is important to have up front. So taking those gaps, we also have a roadmap that we use to define how we're buying those down. And you can see material flammability, fire detection, and contingency air monitor here. Those two bars there are really the Sapphire 1, 2, and 3, and then the Sapphire 4, 5, and 6 experiments. One of the things that we found is we can do the tests or fire experiments on ISS and the combustion integrated rack or the microgravity science glove box, but we found that we really have to look at a large-scale fire to understand what the impact on a vehicle might be. And so that's what we're doing in those Sapphire experiments and why it's a big key to buying down those risks. It gives us the opportunity. We've run 1, 2, and 3, and those were really, we learned a lot, but in some ways they were just getting us to the point where we can, learning to walk. How do we use a resupply vehicle to conduct these experiments? I should note that these were large-scale experiments that were conducted in an ISS resupply vehicle after it left station. What we're looking to do for Sapphire 4, 5, and 6, though, is to expand that matrix and look at more of these gaps. We can run conditions there at lower pressure, higher oxygen concentration, and bigger fires impact the vehicle more so that we look at fire detection. We can have a contingency air monitor, demonstrate the technology that they would want to use on Orion, and really get some realistic data of how that responds in a fire. Also with post-fire cleanup, we want to make a bigger fire so that then we can, mess up the atmosphere, if you will, change the pressure and temperature, and then clean up the atmosphere afterwards. Those are things that will go into Sapphire 4, 5, and 6, but we also have ground-based development, emergency breathing apparatus. Now, it's many of the same kind of sorbents that are in the smoke eater, but that really gets into what does the crew actually have to wear? What can they put on? And then a fine water mist portable fire extinguisher that has been deployed on ISS, but we want to use a smaller extinguisher for Orion. It's a smaller volume to protect. A smaller fire really is what we're looking at from looking at fire sources or potential fire sources in Orion. And so doing those tests on the ground is something that's also going on. So my last slide, we have conducted combustion science experiments on ISS, as I said, in the combustion integrated rack and microgravity science glove box, and that information has been informative, but it doesn't particularly fill some of the exploration gaps. And the whole reason is because the exact conditions that we want to investigate are conditions that nobody wants to produce or experience in a crewed spacecraft. We want certainty that those fire responses are going to work. And so we need someplace else to do that. And ISS resupply vehicles have been, for us, ideal to perform those kinds of experiments. And of course, even though we're not performing them on ISS, they're made possible because of ISS, because we'd never be able to just do a single launch, let's say in a Cygnus vehicle, just to perform a fire safety experiment. There's pros and cons, of course, to doing those experiments. Some of them is we don't have a crew there to change conditions. Right now, we deorbit, and so we burn up every time. But I think that there's also many other types of experiments that might be adapted to that platform if we really get thinking about it. So that's the end of the charts. I guess we're done with the clicker.
Okay. So thank you all. This is, again, a very great overview of what technology is going on. I've got a couple questions, and then maybe we can get some questions out of the audience for the group. But first of all, from each one of your technical areas, what do you see as the biggest challenge that you think we face? I mean, some of you described it a little bit in your charts, but maybe elaborate on it a little bit more and then talk about your approach to trying to solve some of those challenges in a real way. So Robyn, of the environmental stuff, which one do you think is kind of your biggest challenge?
I would pick two. I would pick reliability is overall my biggest challenge, and the thing that kind of keeps me up at night is thinking ahead to when we load up the deep space transport and we're sending the crew off to Mars and we close the door and whatever spares are inside is what they've got, because I would love to send 5 spaceships worth of spares with them. So that's a huge challenge, and the approach that we're using on space station is to get this evolution done and then test for as long as possible. And then the other challenge is closing the air loop. Today on station we're less than 50% closed. We use the Sabatier to react carbon dioxide and hydrogen that's produced by our oxygen generator and form methane and water. And it's fairly easy to separate gas from water and vent the gas. To go beyond that and close the loop further, we have to look at processes that produce longer chain hydrocarbons or even solid carbon. And that's a pretty big challenge in microgravity to separate that out, to deal with the solid carbon. And the technologies we have today that are being sponsored by our Space Technology Mission Directorate and our Advanced Exploration Systems are addressing those, and we have several things in work, but they're still fairly low TRL. So we're putting a lot of effort into that, and we're going to be flying an early flight demonstration, and then with the potential of flying more later on, and then operating as an integrated system.
Okay. Bill, any thoughts? You again described some of them, but maybe you can elaborate on some of them.
So I think the medical systems that I talked about in detail are fairly solvable, but for the first time we're working with the avionics, the vehicle avionics people to integrate our stuff into it, and I trust the reliability, and I think we have enough time to develop all the piece parts and validate those. The two areas that still stand out in my mind, one is behavioral health and performance. We have to have a team that works together of 4 people who will be in a very small environment for a very long time, up to 3 years away from home with long time delays. And it's really going to be a challenge. We haven't any experience in that area before. What we're doing is setting up a number of isolation facilities on the ground. We have a short duration one at JSC, but we're going to have access to the long duration one at IBMP in Moscow, where we'll be doing 4-month, 8-month, and 12-month stays with multinational crews. And we also have access through NSF to winter over stations in Antarctica, which is a more hostile environment to be doing this testing. So this is one of the things that keeps me up late at night. And then there's still, within radiation, I think that we understand the cancer risk well enough, but there are some other risks that we're looking at, degenerative tissue risks, the cardiovascular degeneration, and the CNS that we just don't have enough data on to really know what the impact is. Hopefully, it'll be low enough that it won't be a problem. But so those are the areas that really make me nervous.
And on space station, do you think there's any way we could do some of the isolation things on station, or are they better done terrestrially on the ground?
It's really hard to isolate people on station. You know, I've talked a little bit with the station folks about how we might do that. You know, we're so used that, you know, there's resupply vehicles, there's a lot of visiting crew coming. It's hard to cordon off one module and say these two people have to stay in there for a long period of time. It's hard to take away the cell phones, you know, and the links that they have. Now, I do think that as we get farther along in the program, we are going to be wanting to do some simulations of deep space missions on station where there'll be less environmental oversight and there'll be less communication with the ground, and we have to figure out how we'll do that too. But the isolation is really hard to do there. We'll probably be able to do that for the first time in cislunar space when we start doing the shakedowns of the deep space transport vehicle, because in addition to them being alone in that vehicle in cislunar space, we can implement time delays that you really can't do because of the way the ground control works with the station vehicle.
Bobbie, Gail?
Well, luckily, we stay on the same page because we have the same concerns, right? I would elaborate a little bit on the exploration medical as far as one of the challenges I think we're going to have is determining the level of autonomy, right? What does autonomous mean? How far do we go? You know, how much do we, you know, have to guide the crew, and how much will they know how to do it? We don't need to tell them. We don't need to have them log in and show them that. So I think the level of autonomy is going to be something that we're going to have to work on. And again, that this is a big challenge, the exploration medical, because we are developing a medical architecture. It is not a medical kit. This is, you know, there will be a medical kit, but this is bigger than that. This is a, you know, in the being integrated with the vehicle avionics and being something that's going to really integratedly keep track of medications that's being taken and allow the crew to record symptoms and stuff. And again, it depends on what level of autonomy we go to for that. Radiation, same thing. You know, I think we got the monitoring understood. I think we can characterize the environment. Again, it's the effect on the human body, and we're waiting to see what the results are of the research that's being done. We have it captured on our roadmap so that we know. I think from that, we're going to understand what the effects are, and then it's going to be a risk trade of what we do with that. Again, we're on the same page and share the same thoughts as far as what our biggest concerns are.
And you showed some of the exercise equipment, the next generation stuff like Atlas. It's going to be a lot smaller footprint, a lot more compact. Are there plans to compare the effectiveness of the newer, smaller systems against the more traditional CVIS and
that's what we're going to be doing
ARED
on station.
and treadmill?
We're developing our verification and validation plan in the next few months to start looking at it, and we'll have all our stakeholders involved with us, and we're going to start looking at exactly what the efficacy is of the system and how it compares to the data that we've gathered all these years in shuttle station.
So I think that's a really important thing that can come with station. We've developed pretty effective protocols for bone loss and muscle degradation, and now we get a chance to see that next generation of systems and see if they're as effective, and do we need to change protocols before we commit to this next generation of
Again,
protocols.
and you nailed it whenever you stated at the opening remarks. Again, that's one of the benefits of station is the fact that if we do need to tweak something or change it, we're accessible with the cargo vehicles and stuff that we have today, and we're not going to have that accessibility when we're in deep space. And to build on also what Bill said about, I do believe we need to have dedicated exploration increments on board station. And I would say it's probably to get the ground used to not having the data and the communication like they have today. I think that's even just as more important as getting the crew used to not having it.
Yep. All right, Gary, from a fire safety kind of standpoint, your big challenges?
Sure. There's a couple. One thing that we experienced with in both ISS and shuttle when it was going is conditions that might change, or we want to operate at some other condition than what maybe materials were tested. It's the things that we don't know, or maybe we didn't think that it would be used in that way. You might think of well, we're never going to go to let's say a 36 or something, 100% oxygen. But then further along, you get into development, things start getting built, they do mission scenarios, and it's, boy, we'd really like to. Is it safe? And knowing enough to ask those questions up front, because I said a lot of that gets set up front. And to know what questions we need to be asking and then run those tests, whether it's in a large-scale test or whether we've looked at it enough on ISS in some of the smaller scale experiments. We've got to be smart about picking those out and thinking ahead. The other thing is really just making sure, as Robyn said, when they close the door, that's what they're going to have, that we've tested out fire extinguisher, we've given them masks, we've given them methods to clean up, that those are effective for what we think they're going to find. So that's the kind of the things that so more tests like that, more system tests that we're trying to do.
And you'll get a chance, right, with some of your Cygnus flights in the future to look at cleanup methods and those things?
Correct.
Is that plan?
That's really going to be the focus of those, expanding to look not just at flammability at higher oxygen and lower pressures, but then also detection and cleanup.
Okay. Again, when I look at Station, I think, wow, what an amazing research facility we have to figure out creative ways of doing these things. So let's see if there's any questions from the audience and for the technology folks, and see if there's any ideas or any other questions. So we'll see if there's any questions out there. I see some hands raised.
You can see. I see the blinding light.
I have a question for Robyn. Life support, which is so critical, and you know that the ECLIS system, I don't know what fails and when it's failed and what you had to resupply from Earth, but what is the approach to take something that where you want it to last 3 years with being able to do whatever needs to be fixed on the vehicle? What's the approach? Not being an engineer, I just wonder, how do you start? Are there things on Earth that last a long time that are built that you could use as models to try to look at?
I would say overall, the simpler we can make it and less complex we can make it, then the more reliable it is. I mentioned when we first flew our regenerative ECLIS system to space station, it was pretty experimental, and we had to go through a lot of safety reviews. Our oxygen generator takes water and breaks it into oxygen and hydrogen, and those are flammable. They get mixed together. So the safety community was rightly so very worried about it, and as a consequence, we had to put it in a big dome, and we had to add a big purge system and all kinds of sensors. And while that makes it very safe, it also makes it very complex. Unfortunately, our oxygen generator has been very reliable. But overall, I'd say trying to reduce complexity, but microgravity works against us there. Our urine processor, if you were to distill urine on the ground, you'd put a pot of urine on your stove and the steam would rise and you condense it and there you go. In microgravity, that doesn't work that way. We don't have gravity to separate phases, so it's a big centrifugal rotating drum, and that's very complex. But overall, that's our approach, and then just testing and learning and tweaking the design and testing some more.
And Robyn, what do you think about biological systems and plants for life support? I know that gets discussed sometimes.
We get asked that a lot. We have looked at biological systems. We have a whole group that continues to look at those systems and develop those. In general, for a transport kind of spacecraft, we don't really have the space to use plants for life support. I think they're a great idea to use for supplemental nutrition, and you guys will need it.
Behavioral health.
Yeah, but
Right.
a whole wall of it, I don't think
But
is
we
going
don't
to be
have enough-
practical, which is what
Right.
she needs. We need it, like you said, for behavioral health and for supplementing the nutrition and the food that we're going to be flying.
When
but-
we get to a surface, it makes more sense because you'll have more space there. And also, we worry about, something happens to the crop. We also have to have backup physical chemical systems.
Again, we're integrated.
Yep. Great. That's good. All right, more questions?
Good afternoon. My name's Larry Pollack. I'm with the Department of Defense, and this is my first time to this conference. One of the things that brought me here was to see what technology requirements NASA requires as you move forward to more complex missions. And a lot of the things that you talked about in this panel have had significant amount of research already conducted in areas, for example, water recycling, antimicrobial clothing, personnel masks for smoke situations, particle detection, pathogen diagnosis and identification, just to mention a few that I jotted down while you were going through. So the question is, do you look at market research of recently completed research or even ongoing research, depending on its technology readiness level, to be able to leverage the investments that, for instance, the Department of Defense is making, where you would be able to use the same technology because the warfighter, our customer, has similar requirements, particularly when it comes to the reliability, the ease of operation, size, weight, and power. Thank you.
I think Bill
Yeah,
would be the best.
I think we spend a lot of time trying to understand what's going on in other places. We have a number of connections with the military, and we're working together on some projects with the military. We invite them to invite various folks that we work with in military R&D areas to our annual meetings, and we go to their annual meetings to try and compare notes and to try to figure out how we can move together. There's always better ways to interact, but we're doing the best we can right now, and we have probably in the last 6 months we've had 7 or 8 separate meetings with our groups, with different military groups that are working on similar problems for the warfighter.
Robyn, there may be some areas too that I know that you've interacted with.
Right, and the life support systems, particularly submarine, is a closed environment, and we've worked with DoD and compared technologies. Our oxygen generation system is very similar to what you have on submarines, and we've looked at CO2 removal systems, and we have lots of touch points there, contaminant removal and monitoring systems. So, yeah, we try to stay up to date on and share knowledge back and forth.
And we've done the same thing with environmental monitoring, but especially looking at combustion products and technologies for that we've worked with submarine community and also with fire suppression.
And same thing with some of the masks, right? The smoke eaters, some of those things. Again, you've grabbed that from either the commercial
Correct.
side, DoD, or fire.
And we're
folks.
talking just now because specifically talked about the military and bringing that out, but we do market research, right? We have several tools that have been developed for the agency that we use to go out and do searches as we're looking for technologies.
Okay. Yep. Another question out there?
Yes.
Yep.
Hi. Thank you very much for a great panel discussion. My question pertains to radiation, health effects on astronauts. And it seems like you were mentioning that we have a better understanding of cancer as far as radiation is concerned, but some of the studies that have done on radiation are either extrapolations from Hiroshima or some other very strong events, or even if you try to look at studies with radiation through CT, where it might be larger amounts of dose for short amounts of time. Are there any studies that have been done on astronauts that have been living for a longer amount of time and how their body has reacted?
The radiation environment in deep space is a fair amount different from the radiation environment in low Earth orbit, and yes, the medical community keeps track of the late-term effects of radiation on the crew members. They monitor it fairly carefully. For us, we use rodent models for a lot of our work. We have a simulator that we've worked with the Department of Energy at Brookhaven National Laboratory to develop, where we can simulate galactic cosmic rays, so the heavy particles that are going to cause the most damage on these kinds of missions, at least what we think will be the most damage, we can put, and now we can actually have them come in parallel to one another, actually in quick shifting series, so we can create the full spectrum of galactic cosmic rays and irradiate these rodents with them. We also are looking at the advances in terrestrial medicine and terrestrial care for cancer in particular. And there are very rapid advances in those areas. And we're beginning right now to solicit for the first set of studies that will be looking at countermeasures to some of the untoward effects of radiation. So pharmaceutical countermeasures that we would fly along with them.
And we're doing a lot of things to understand the radiation environment. The alpha magnetic spectrometer on board station is a very interesting device because we knew the basic radiation environment, but we didn't know the distribution of heavy ions and some of the larger, really high energy particles that aren't even shielded from our magnetosphere. But AMS is able to look at those, and now we understand those profiles. Then Bill can start altering some of their animal studies to mimic those profiles to see specifically what may be coming about. It may not only be cancer, as Bill was discussing earlier. There could be other medical concerns associated with a different profile than we've been testing to in the past. And I think the other area we're doing is we have a radiation monitor on the surface of Mars on the Curiosity rover today. So we actually know the Martian radiation environment, and we can see what it looks like. It's surprising in the fact that the very thin CO2 atmosphere on Mars provides a significant amount of shielding for radiation. You know, if you look at kind of just a generic kind of order of magnitude, roughly the radiation environment on space station is roughly about the same as the radiation environment on the surface of Mars. The big problem is the transit phase, where you have no shielding other than what's in your spacecraft, and then it's this storm shelter discussion that Bobbie Gail was talking about, where we look at what we might do there. Is there some kind of active shielding we want to put in place, you know, with superconducting magnets, et cetera? But those become very cumbersome, and they don't fit in the smaller size spacecraft we're trying to build.
But it's continuing to evolve, and we're continuing to learn more and more.
Yep. But again, I think the neat thing is these are areas, when we identify these risks, we then turn loose the entire NASA team. We search the community to find creative solutions. You know, the innovation beyond boundaries, little words in this conference, are what we're trying to do every day with all these technology challenges. So thanks.
Yeah, and as a matter of fact, we set up a special external institute to use innovative approaches to finding game-changing technologies and approaches to solving these problems out there. It's called the Translational Research Institute. That's been in place since October. They've had their first solicitation this year, and they have proposals that they're reviewing for game-changing technologies to help specifically with the risks that we have to deal with for exploration.
Hi, Paula Korn. I'm doing research currently on travel and living on Mars. And when the fire safety issue came up, I became curious, really. I know you've done some fire tests on station, combustion, and so forth, but all of a sudden I was thinking about Apollo 13 and immediate problem solving to bring 3 men back alive. I was wondering if there have been any lessons learned, or if they're applicable today. It's a long time ago, but any references there to our experience?
I can't say directly for Apollo 13 or lessons learned, but again, I would get to understanding the environment that we're going to put them in. You might think that, okay, it's partial gravity, so maybe that's going to look a little bit more like, normal gravity. Smoke would rise, so you have a little bit more idea about where to put, smoke detectors. But the thing is that when you look at, material flammability, it can actually, at partial gravity, between the balance of heat release and convective cooling, things can be a little bit more flammable in partial gravity than they are either at zero gravity, force flow, or in 1G. Thinking of things that of lessons learned, were you thinking of lessons learned to return them, or?
Well, in the event of a fire in travel.
So what you're doing is characterizing it.
We're characterizing what the risk is and then providing the tools so that they have some way to respond to that risk, if that would occur.
Again, the way I would kind of simplify it, and Gary, you can help me, is the first thing is we're trying to prevent fire, right? So we're understanding all the conditions that could cause a fire. So we're actively looking to understand combustion properties, how fast things burn, et cetera, how we can prevent fire. Then Gary's starting to look at extinguishing techniques to make sure that we really understand how to effectively fight a fire or put a fire out in the fastest manner that we can. And those are some of the experiments they're starting to look at.
Sure.
You know, are our fire extinguishers, you know, we're now flying some new misting fire extinguishers. You could probably talk about those better than I can on station. They're a water-based system, and that we've determined, I think, is maybe more effective in fire suppression.
It's more effective for the breadth of fires and probably some of the more likely fires. One of the things that we really look at is electrical or battery fires, some type of an energetic fire source like that. CO2 doesn't do much with that at all, because you've got to really remove some of the heat. And we found that water mist, or fine water mist specifically, does a good job of extinguishing those. And so that's what we're deploying. But then we've got to make it, I would say, Orion size it, so that we're not carrying more than what we need, but we're carrying enough to fight the fires that we have.
Then the next piece is, after it's extinguished, how do you clean up the environment such as you could kind of continue on your journey? The problem with Mars is, it's like Robyn described, you're kind of committed. Once you do that burn towards Mars, you're going. It is not easy to do some kind of plane change. There's not a free return available to you that's any time of reasonable duration. So it's going to be really hard. So whatever you deal with, you got to figure out how you can mitigate it and get you back in a safe configuration to continue on your journey. Maybe another question in the back?
Hello, thank you for an interesting and diverse panel of experts. And I had two questions. My name's Adrienne Provenzano, and I'm a STEAM educator, which means I connect arts and humanities into STEM fields. My sort of two-part question is, are you looking at all at historical terrestrial expeditions like North and South Pole and other extreme environments to get any ideas of what's going on station and going out into Mars, if that informs you at all? And then probably especially to behavioral and team issues. And then as far as the imaginative idea of the Hermes, what is preventing us from building something half as big? Is it just a matter of funding, or is the idea that at this point, let's do a good job with something small, and maybe that's 50 to 100 years out? Thank you.
So the answer to the question about do we understand previous expeditions from previous centuries is yes. We spend a lot of time, our behavioral health and performance experts spend a lot of time trying to understand what worked and what didn't work, and what the success, for those that were successful and for those that failed as well. There was a fellow called Friedholm Nansen, who one of our behavioralists told stories about to our group for 2 or 3 years. It was a fascinating story. He was trying to get to the North Pole and lost his whole crew and ended up getting back, but it took him almost 3 years, if I recall, to get back. A lot of us know about the Endurance and Shackleton and that group, but the behavioral health folks are spend as much time as they can understanding things, and even the experiences from the military. Some of our folks go back into the military, and we can understand things that might not be available to the general public. So we use that very carefully. I think that for the second question, I probably should let Gerst answer that.
So again, what we need on those charts is we need not only a Hermes and a deep space transport, but we'll stick a station on there next time, and then that will give you a feel for where these things fit in overall size. What we chose for deep space transport is it essentially can be launched dry without any propellant and any systems on a single SLS launch. So we're planning roughly 2027 to launch this spacecraft as a single entity. And the reason we want to launch it as a single entity is we want to really optimize the mass, because you have to, whatever structure goes into this thing, you have to accelerate out of some gravity region between the Earth and the Moon towards Mars. And that's very expensive from a propellant standpoint. Then once you get to Mars, you got to then take that energy back out, and you got to go into orbit around Mars, and then ultimately, if you want to land something, you'll carry that with you, or it'll be pre-positioned. So the point is we need to minimize the amount of mass, and that's what's really driving us to keep things small. And we chose Deep Space Transport as a single entity, so we don't build it up like Deep Space Gateway, where we have a power propulsion module, we have a habitation module, we have a logistics module, or a space station where you saw all the pieces come together. There's hatches between those, there's interfaces, there's structural pieces, all that adds weight. So the idea with a single launch of the Deep Space Transport is we can optimize that entire structure to be the minimum amount of weight. And then it still takes roughly 3 or 4 more SLS flights of just pure propellant and logistics to get the Deep Space Transport actually ready to go to Mars. So you see the vehicle itself, but then all the other logistics and all the stuff that's got to go inside, even though we're trying to make it small and miniaturized, is roughly 3 or 4 more flights. So that scope tells you how difficult it really is to get something to Mars. So when I see these movies with these great big things and these rotating centrifuges, I just cringe because I go, they're going to tell me to build one of these. There isn't enough time, nor money, nor effort to really put this together. So it is the fiction side. It's somewhere maybe we could get there in pieces, but we'll put Station on there, and then you recognize Station took us, 30 flights and a bunch of years to put together, and then you'll get an idea and then you have to accelerate that 900,000 pound thing out of the gravity well towards Mars, and that is not easy. So that's why I think it's interesting, it's something we'd like, but I just don't think it's really practical with today's technology. Now, maybe nuclear propulsion can come along, maybe there'll be other materials, other things that can help us with that, but with today's technology, we've got to go on the smaller side to make this a reasonable thing that we can do within the 2033s, 2034 kind of time frame.
No, and Bill, if I could add on to something before that, the discussion now we're talking about human factors and behavioral health. One of the things that we're really going to be working on is a lot of times folks think that, behavioral health and stuff is, I'm bringing some photos from home, I'm bringing some pictures and stuff like that. There's a lot more than that. And there are some really simple things to do that can make the environment inside a habitat pleasant. Wood grain type look and things and feel, paint colors, things like that. And those are the things we're trying to introduce early on as we start talking to the folks formulating these vehicles and stuff that sometimes get that afterthought. And so we're trying to work really hard to integrate all of that as we move on to again, kind of a lessons learned, maybe not from far away, but still.
And I'd say another thing that I think is really important that Bill can maybe add on is for the behavioral health thing is to have really productive work for the crews to do. On Station, we have an unbelievable amount of research today. You got to see Kate's DNA sequencing, you get to see all this variety of science. You're going to launch to Mars with whatever science you've got, and how do you keep the crew engaged and productive for that extended period of time? I think that's a key driver in terms of overall behavioral health.
Hopefully not fixing the ecosystem.
Not fixing the ecosystem and not exercising every day.
Boredom is one of the key things that could drag down the whole mission. So keeping them interested in things to do and having a lot of stimulating things to do, whether it's work or study or something else that we can send along with them.
And we're working on that. There's going to be several workshops occurring to where we're starting to define what science we would want to do. There's several folks out here that I'm looking at right now that are on that panel with us, and as we're looking at what we'll define for deep space as far as science.
And there's another challenge with Mars that doesn't get talked about too much. We're about ready to go into a period where there'll be no communications with the rovers on Mars for about a 2-week period. It starts the end of July. Mm-hmm. So it turns out that the sun is between Earth and Mars. And so unless we have some kind of communication relay that is in some significant elliptical orbit around Mars, there's going to be a 2-week period throughout the year when there really is no comm with our crew. And so that's going to be, you talk about isolation on the surface of Mars, that could be a big deal when that period comes about. And that's something else we need to think about in this overall situation we're trying to deal with.
Yeah, when you think about it here, if you're from where Bobbie, Gail is in southern Louisiana, they put people in boxes like that for long periods of time when they've been dead, right?
Oh, that's not good.
So true. I can't even argue that.
Now we've offended everyone from Louisiana.
That's right. Now that you've offended my entire people, my people. Well,
All right, so I know.
That's right. Oh, that's right.
So
Thanks
all
for
right,
me,
well,
too.
we got maybe time for one more question or maybe two more questions. Okay, go.
Thanks, Bill. Great job, by the way. You guys have covered the waterfront, and obviously a lot of good work going on, and I appreciate that. I'm Frank Culbertson, by the way. And Bobbie, Gail, if you want to put wood grain up there, I think you ought to think about fuzzy dice and stuff like that, too.
You think that maybe the
Or maybe a fuzzy
disco ball?
Yeah.
Is that, whatever you need.
I appreciated the question about looking at other programs, other parts of the government, other parts of the community, and what they're doing and how that can be applied. And I know you've been looking at that. I have two questions, really. One is, if this group that is very much involved in research and development could come up with one killer app, do any of you have any one thing you'd really like them to be working on because you can't afford it or don't have time or whatever, but they, due to their curiosity and interest and resources, might be able to come up with something? Is there something like that that might help you? And then the other part of my question is, given the fact that it'll probably be at least 10 or 15 years before we're able to send this crew out on this expedition, and we will have made a lot of advances, continue to make advances in miniaturization, data processing, computer power, are you looking at increasing autonomy for this mission so that they could, in fact, be totally autonomous for even more than the 2 weeks you're worried about, if they needed to be in terms of AI, helping solve problems, et cetera? Thank you.
So, from my perspective, I think, the lecture we heard earlier from the guy from IBM who was talking about Watson and how he wants to improve Watson to be, keeping track of the whole environment and to be able to interrogate, a device and say, how do I fix you? And have the device be able to speak back. Those sorts of things would be very useful, not only from the health and performance perspective, but also, I would imagine, from the engineering perspective, because the crews are not going to have enough time to train fully on all these systems. And then on a 3-year mission, their last training will have been, 3 years before they get back. So if something's happening on the way back, yeah, so they'll be spending time doing that. Yeah, so I think there's a lot there, and so I see the apps as being integrative apps that are intelligent and can help to start where a person's knowledge leaves off and help to walk them through problems. From a medical perspective, that's also very important. How far we can get along with helping people do procedures that are not trained well for those procedures is a good question, and how much that will advance in the next 10 or 15 years is a good question that we keep looking at. Did you have any?
Well, that was the same thing. It was Exploration Medical, that whole entire architecture, right? We've got several modules of it that we need help with tackling. And so that could be a whole nother conference that we talk about it.
I was going to mention 3D printing. There's we're doing a lot of experiments with 3D printing on the station today, and we're making tools and things. I get asked a lot about 3D printing for spare parts for life support systems, and I get a little skeptical because, suppose a bearing in my pump fails, and I could print that, but could I do the precision disassembly and assembly required with all the tight tolerances to really make that pump, put it back together and make it work? So the killer app I would be looking for is figure out how to use 3D printing to really do some of the complex parts that I would need that would be more prone to failure.
One of the things that Bill just said that I thought of when he said it was, it comes from a fire prevention kind of standpoint. Nothing ever just bursts into flame because it was, it felt like it. There was some failure. There was something there that was happening. And so being able to either have ways to interrogate, how it's performing, or for it to be able to tell you, that something is wrong. And to keep something from failing, overheating, shorting, all those kinds of things. I think that's something that the best thing for fire safety is never having to worry about it.
Yeah, very good.
And again, I think the thing that's really important is we keep an architecture and a plan that's open enough that as new technology comes on, we can insert it relatively quickly. So, Bobbie, Gail's discussion of the radiation sensors, right? We had these big, huge devices. Now you can get them as small as she's describing. Now we can embed them in the spacecraft. We never thought about that before, right? Or if the 3D printing's coming online, what can we really print? I see that, I had a discussion once on the behavioral side, and I talked about the crew members, and I go, well, why do I want to do a video conference, or why do I want to send a picture to my crewmate or my loved one on orbit? I'll design a little trinket for them, and I'll have it printed on board station, so then they can actually have a gift on station from home. So whoever thought you would use 3D printing to be part of behavioral health and performance, right? But it could be. Those simple things that we take for granted, how do we take this technology and extrapolate it in a creative way and create an architecture or a system that, we got this new idea, but shoot, we built the spacecraft. Now we can never put it in the spacecraft because it's going to take us 3 years to redesign the spacecraft around it. How can we figure out a way we can keep our architecture open enough we can take creative ideas, absorb them into what we're doing to do these challenges? Because this is truly a huge challenge. When we describe the Mars mission, it's easy to see it in pictures, but when I look at the engineering challenge, it is monumental, but it's exactly what we ought to be doing. And that first step in that is really station. I mean, station is amazing in itself, but how do we use station to then extrapolate more to that Mars environment? Maybe one more question, and we'll call it a session here. So there's two here, I think, right in the middle, maybe. If we can get a mic there. Maybe we're out of time and the microphone people have left us.
I got to stand
shout.
up.
My question goes back to the radiation and in relation to the long mission to Mars and in relation to the solar cycle. Which is the lesser of the two evils? So during the solar minimum, of course, we have less solar-genic radiation, but then we are more open to the galactic cosmic rays versus then with the solar maximum, we have way more solar-energetic particles.
Okay, so just so everybody can hear the question, just to make sure that the question was basically the solar min and solar max, what is the best strategy to minimize the radiation environment to the human, to go during solar min or solar max?
Yeah, so we can shield solar particles. We know how to do that, and shielding works very well for that. For galactic cosmic rays, the shielding can only be so thick, and then it starts generating secondaries that are as harmful as the primaries if they got through. So we would prefer to be going at solar max so that we could minimize the GCR exposure.
Yeah, that's kind of counterintuitive when you think about it, right? But the heliosphere shields you from the galactic cosmic radiation, which we can't shield from. So then that's the logic. Now the problem is it turns out the solar maxes appear to be decreasing in strength, which is not such a good thing for us because we were counting on them being very strong, which also seems really weird. But that's why we're counting on those being strong. So we just got to watch the solar trends and make sure solar max stays at about the same level, or we have trouble with the galactic cosmic
We can't
radiation.
shield from yet.
We can't shield from yet. And that's another area maybe in this things we hope for. Is there some shielding technique that can actually shield us from those? And we'll see. So again, I want to thank all these folks for being here and all the work they do every day. Hopefully they gave you some things to think about, some ideas to share. You'll see them throughout the conference. Ask them really hard questions when you see them walking around. Ask them how much fun it is to work on Space Station, what they enjoy every day and in their office, how much they interact with each other, how much they're really integrated. Ask them how much they like each other, those kind of things. Really poke on them hard. See if you can tease out that behavioral health and performance issues with this panel and see if they're really up to snuff and they're really ready for that Mars mission. So your job is to test them through the conference. So poke on them, see if they're up to the technology challenge associated with Mars using Space Station to go forward. Thanks.
Thank you.